Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to take what we've learned from resonance and formal charge, and now we're going to apply it to organic molecules. And the thing about organic molecules is that they are huge. They tend to be larger. We're not going to be dealing with like very large molecules, but they tend to have multiple central atoms where you have atom connected to atom connected to atom in like a chains, right? And so you're going to have, when you have multiple central atoms, then you're going to need to know how to connect those together. And the great thing about organic compounds is that oftentimes their formulas are written in such a way that it actually will tell you what the structure is. You just need to know how to read the formula. And so I'm going to go over that today. In addition to how do we figure out the resonance structures for our organic molecules. And the thing is, it's no different than what we've done with any other molecule in other videos that we've done. So, first, let's start with this molecule here. So the way this formula is written, and you can write organic formulas in different ways, but this is a really good way for writing because it tells you the connectivity of the atoms in the formula when you write this way. So notice that you'll see that the hydrogens follow this carbon here. And normally, again, we know that hydrogens only bond once. The hydrogens aren't going to be connecting these together. So in reality, what this is telling you is that these three hydrogens are bonded to the previous atom. And that previous atom in this case is the carbon. And of course, this next atom, the following atom after the hydrogens are also going to be bonded to that carbon. They're not going to be bonded to the hydrogen because the hydrogen is already bonded to the carbon. So in order to connect these, nitrogen has to be bonded to that carbon as well. And then the oxygens, the oxygens are also, you can figure out what they're bonded to because again, the oxygens are going to be bonded to the nitrogen or the previous atom that the oxygens are follow. So in that case, the nitrogen. So the structure of this would be the three hydrogens bonded to this, right? And then you've got the nitrogen bonded to the carbon. And then you've got the two oxygens bonded to the nitrogen. So this would be our skeletal structure for the organic molecule. Now the first step, I skipped the first step for how to figure out the Lewis dot structure for the molecule, and that is you need to sum up the total valence electrons for the whole molecule. So if we sum that up, we get 4 from our carbon because it's in group 4, 1 from each hydrogen because hydrogen is in group 1, 5 from the nitrogen because it's in group 5, and we have oxygen. Oxygen is in group 6. We have 2 oxygens, so that's 12 from the oxygens. So plus 12. And we add that we add that together and we get 24. So 24 electrons total. How many did we use when we created our skeletal structure? We used 1, 2, 3, 4, 5, 6 bonds. So 6 times 2 is 12. So we're going to remove 12 of them and we get 12 left. So the next step is I'm going to add lone pairs to all the outer atoms. Now, my central atoms, I have 2 central atoms. I have carbon and nitrogen. So my outer atoms are here. So my hydrogens are okay because they only need one bond. So I'm not going to give them lone pairs. But my oxygens don't have an octet. So I need to give them lone pairs so they can have an octet. So I'm going to put 1, 2, 3. And I'm going to put 1, 2, 3. So I've used how many electrons when I did that? So I have 1, 2, 3, 4, 5, 6 lone pairs, so that's 12. So minus 12 electrons gives me 0. I have no more electrons left over. Okay, so what do? I check my molecule to make sure everyone has an octet. So I have duets for my hydrogen, so that's good. My carbon has 4 bonds, so that's an octet, that's good. And my oxygens both have 1 bond and 3 lone pairs. So that's going to be 8 and 8. But notice my nitrogen here. My nitrogen only has 3 bonds to it. So what I need to do is either this oxygen or this oxygen, I need to move lone pairs to make a double bond. So I'm going to take this one and I'll move a lone pair there, and I'm going to get a double bond. So then this becomes C, so H, H. Well, why don't I just erase this? So I got a double bond there. So this would be the Lewis dot structure for this molecule here. So now, but you'll notice that I could have resonance here. And the other thing I want, so here's the resonance. And so I can draw another one, but instead of having the double bond there, I can have the double bond there, because these 2 electrons can move, create a double bond, and these would be moved out. So I have, I can draw it this way. Oops. So that would be the other resonance structure for this molecule. And so, I can use formal charges, right? So here again, let's see which one is the better one. So again, each of the oxygens are going to have 0 formal charge because they meet the duet rule and they have their bonding. They have their bonding patterns. And again, you can calculate the formal charge by formal charge is equal to the number of valence electrons minus non-bonding electrons, your lone pairs, minus 1/2 the bonding electrons, the electrons in the bond, which is again one electron per bond. So carbon has 4 valence electrons, no lone pairs. It has 4 bonds, so 1 for each bond. So, and this is the bonding pattern for carbon. So we would expect that to be 0. For oxygen, for this oxygen, it has 2 bonds, 2 lone pairs. That fits the bonding pattern for oxygen, so we would expect that to be a 0 formal charge. Here, it doesn't fit the bonding pattern, so if you know that this is a -1 formal charge from the bonding pattern here, you could do that. Or we could just calculate it out using formal charge equation. So here it's going to be the valence electrons for oxygen, which is 6, minus the number of non-bonding electrons, which is 6. I have 3 lone pairs, minus 1 from the bond, minus 1. So then the overall charge on this is -1, as I predicted. So it's -1 formal charge there. And then here nitrogen has 4 bonds, no lone pairs. And so again, you might expect that to be a +1 if you know the bonding, the common bonding patterns. But we can calculate it out again. So 5 for the valence electrons of nitrogen, because it's in group 5, has 0 lone pairs, so no electrons subtracted for that, and it has 4 bonds, so 1 for each bond. And so that gives us a +1 charge, as I said it would. And so that's it there. So then we can do the same thing here. Everything else is the same. The only difference between this one and this one is that we switched to double bonds. So everything else here is going to be the same. 0 for the hydrogen, 0 for the carbon. It's going to be 0 for this oxygen, -1 for this one, and again, +1 for that one. So notice that we have resonance. Both of these are going to be equally important because they're exactly the same. They got exactly the same number of formal charges, the same low number. So this one has 2 1s. This one has +1, -1. And so they're exactly the same except for where the formal charges are located. So, so these would be equally important in this regard. So for this problem, I'm going to do this more quickly. So we have CH. These 2 hydrogens are bonded to that carbon. So we're going to bond the hydrogen like this. And this nitrogen is bonded to this one. And the thing about these 2 nitrogens is these 2 nitrogens are bonded to each other. So we're going to bond them like that. So this would be my skeletal structure. And again, we need to find the total valence electrons here. So here we have carbon is 4 valence electrons because it's in group 4. 2 hydrogens, so we're going to add 2 for those. And then nitrogen is in group 5, so we have 2 of them, so that's going to be +10 for the nitrogens. And that's going to give us a total of 16 valence electrons. So now how many did we use to create our structure here? We have 1, 2, 3, 4. So that means we used 8 electrons. Subtract out 8, and we have 8 electrons left over. So now we need to put those electrons in. The hydrogens are fine. And then this is our central atom. These 2 are going to be more of our outer atoms. So we're going to add 2 here, or 3 here. So we have 3 there. And then we add 1 here because we ran out. So we have 6 and 8. So we used up all our electrons. So now it's a matter of checking to make sure we have our octets. So here we need an octet here for carbon. Carbon wants to have 4 bonds. So we're going to have to move these electrons to make a double bond here. So we're going to take these and move them there to make a double bond. So let's erase this, and we'll have a double bond there. So now carbon has 8, and that's good. So everyone has 8 except for this nitrogen here. So for this nitrogen, we'll have to move an electron pair here. So we'll have to move, this one is fine, so we'll move that one and move it there and make a double bond. So let's erase this, and we'll put a double bond there. And so now if we check, everyone's happy with an octet, hydrogen's happy with a duet. We have 8 electrons here, 4 bonds. We have 4 bonds here with 8 electrons, 2 bonds, 2 lone pairs, 8. So this is a good Lewis dot structure. But is it the only Lewis dot structure? in the next video, we'll cover that.